In this lesson, we're discussing universal gravitation, a big, important scientific idea that was first actually written down by a guy named Isaac Newton. We've talked about Newton before in the context of the laws of motion and why objects move the way they do. What Newton was trying to do when he ended up coming up with the big idea of universal gravitation was to prove a set of laws that are known as Kepler's laws. And what Kepler's laws were, there were three of them, they were simply observational laws that predicted the motion of the planets. Kepler had no idea why those laws were the way they were. They just worked based on him finding out what the pattern of the planetary motion was. So Kepler's laws were very successful, but nobody could really explain them. And that's what Newton set out to do. The story goes is that he was sitting in an apple orchard and an apple hit him on the head and he came up with the idea of gravity. And that's not really correct. But at the point where he discovered the idea of gravity, he already knew the three laws of motion that we've discussed, and he also knew about centripetal forces, meaning that in order for something to be turning, it has to have a force acting on it. So because the planets are in motion around the sun and they're turning around it, he knew that centripetal forces were involved. He was sitting in an apple orchard, and so the idea that he has is that the Earth is what's causing things to be pulled towards it. So in the case of an apple, sitting in an apple orchard, that's what he was looking at, he had the big idea that the Earth itself is what causes apples to fall. In other words, there's a force between the Earth and the apple. So the Earth pulls the apple pulls the Earth. That's just Newton's third law. So because apples are pulled towards the Earth, his big idea was the Earth is what physically causes the force. Now, since apples, no matter how tall the tree gets, are always pulled towards the Earth, Isaac Newton figured that this force extends out forever, extends a long way, possibly all the way to the moon. So, by reasoning, since the highest apple tree, apples still fall to the ground, Newton figured that maybe the same force that causes apples to be pulled to the ground extends all the way to the moon. And so that force is what causes the moon to move in a circle around the Earth. So remember, we need a centripetal force in order to make the moon turn, so that force could be caused by the Earth. If there wasn't a force between the moon and the Earth, then the moon would just keep moving in a straight line at constant velocity due to its inertia. So Newton took this one step farther. He said that since the Earth pulls the apple and the Earth pulls the moon, obviously by Newton's third law there has to be a reaction for it. So the Earth pulls an apple, the apple pulls the Earth pulls the moon pulls the Earth. That's simply Newton's third law. Well, because this force seems to be involved with all objects, because all objects have to exert the same force back on the Earth, Newton's really big idea is that maybe this force exists between all objects. So if the Earth pulls an apple, apple pulls the Earth pulls the moon pulls the Earth, maybe the moon also pulls the apple, and the apple pulls the moon. Newton referred to this big idea as gravitation. His big idea was that everything pulls everything. Put it in more fancy terms, all objects exert a force on all other objects. So right now, all the objects around you are being pulled towards you, and you're being pulled towards them. So because it exists between all objects, we refer to it as universal gravitation. All objects in the universe exert an attractive force on all other objects. Key word is attractive. It pulls towards it. This force is caused by mass. So because you have a very small mass relative to the Earth, your gravitational force on other objects is very, very small. So it's a very weak force. There's only 3 objects in your world that are strong enough to actually exert a gravitational force you might notice. Those would be the Earth, the Moon, and the Sun. The only reason you notice the moon and the sun's gravitational force is through things like tidal motion, waves, tides coming in and out. This force gets smaller with distance, so things that are far away aren't going to pull as hard as things that are close. So for instance, Mars is only slightly smaller than the Earth, yet it's so far away you don't notice its gravitation compared to the Earth. Jupiter is a lot bigger than Earth, but it's even farther away. So the farther away you are from the object, the smaller the force is. So Newton's the one that gave this force the gravity name. In Latin you would say gravitas, which means weighty. Nowadays we just say gravity. So the actual size of the gravitational force depends on two things. Number one, it depends on the mass of both objects. In equation form, we'll call that m1 and m2. It also depends on the distance between the two objects squared. We'll call the distance d. So we can write an equation like this. We can say that the force of gravity between two objects is the product of the masses, m1 times m2 on top, over the distance between them squared. So remember, distance getting bigger makes the force of gravity smaller. Now in order for our answer to come out in newtons, we need some sort of proportionality constant in that equation. So that proportionality constant, we're going to give the symbol big G. It's called the universal gravitational constant, and we're just going to put it right in there. Now we have this equation. The last thing that we need to do is actually figure out what the size of big G is. It doesn't depend on anything more fundamental. It's something that we have to measure. So the guy that measured this for us is a cat named Henry Cavendish. He came after Isaac Newton. Newton never actually knew what the value of big G was. But Mr. Cavendish measured big G, and he used an apparatus that looks something like this. From the ceiling, he tied a string to a large, heavy barbell. So you have two masses on either end of the barbell. And then on the string, he put a mirror. And the reason that there's a mirror on the string is so that you can use light reflection to measure how much the string twists. So he then takes two other masses and puts them on either side of the barbell masses. So that's the things in blue there. One in front of the barbell, one behind the barbell. So when you put those two other masses on either side of the barbell, the very weak gravitational force still causes a small attraction between the blue masses and the black masses, which causes the string to twist. You measure this twist with the mirror, just reflect the light off the mirror and see how much it moves, and from that you can figure out how strong the force of gravity is between the black masses and the blue masses. So it's a very difficult experiment to do because the force of gravity is so small. And again, this is back in the 19th century when this is actually happening, so the technology wasn't as good as it is today. But Mr. Cavendish was still able to measure this very, very accurately. In fact, we haven't improved on his experiment at all. And the value that he got is a value of 6.67 times 10 to the negative 11, which is a very, very small number. The unit is Newton time meter squared per kilogram square, so that when you substitute it into our equation over here, your answer comes out in newtons. So here's a real simple example. Let's say that you have two rather large asteroids, one that's got a mass of 50,000 kilograms and the second that's got a mass of 100,000 kilograms, and you put them 10,000 meters apart, which is really, really small on an astronomical scale. The question is, what is the force of gravity between the two asteroids? So we take our gravitation equation, we have both masses, we have the distance between them, big G is a number that's given to us, and so all we have to do is just substitute. So substitute G, our two masses are 50,000 and 100,000, and our distance is 10,000, and we need to square that. And when you crunch all those numbers, you get 3.3 times 10 to the negative 9, and that would be in newtons. Unit for force is still newtons. So that's like a ridiculously small force. You would never actually be able to notice something that small. The experiment that Mr. Cavendish did, that we discussed a few minutes ago, is often referred to as weighing the Earth, or more correctly, massing the Earth. The reason is that once we know the value of big G, we can calculate the mass of the Earth. It's kind of exciting because there's no other way to actually measure how big the Earth is. We can't just put it on a balance or something like that. So what we have to recognize is that the equation Fg equals gm1 m2 over r squared is essentially the same as the old equation that we used to find weight, which is just mass times little g, the acceleration due to gravity. So by setting those two things equal to each other, letting m1 be your mass, it's going to cancel out here in just a minute, and m2 be the Earth's mass, then we can write this, where we say gm1 m2 equals, or over the distance squared, equals m1 times little g. So the m1's cancel out, we get this. All the things we know what little g is, 9.8 meters per second squared. The distance between you and the Earth would be the radius of the Earth. So that's why instead of a d, I wrote it as an r. It's the radius of the Earth. And the radius of the Earth is actually easy to measure too. It's 6.38 times 10 to the 6 meters. How do you do that? Well, there's several different ways. One way is to know the distance between the Earth and the Moon and measure the shadow on the Moon during an eclipse. That's one way that you could do it. So solving this thing for m, which is what we want to know, the mass of the Earth, we get mass of the Earth equals little g times the radius of the Earth squared over big G. So plugging in our numbers, and then do the arithmetic, and you get the mass of the Earth to be 5.98 times 10 to the 24th kilograms, which if you looked it up in the front cover of a physics textbook or a table of information, is the exact same value that you would find there. So we knew the mass of the Earth way back in the 19th century, before we had satellites and more advanced measurements like that. And as it turns out, we actually need to know the mass of the Earth before we can put satellites in orbit, or put a man on the moon and things like that. So a very important concept, very important number that we needed to know in order for science to progress forward. So the big idea of Newton's law of universal gravitation was really important for explaining why planets move the way that they move, why the tides are affected by the moon and the sun and things like that. And it was also critical for things like putting a man on the moon, launching rockets, weather balloons, those sorts of things. So, big important ideas to remember here. The gravitational force depends on the mass of both objects. So if you double one of the masses, then you're going to double the mass, double the force of gravity between them. If you double both of the masses, then you're going to quadruple the force of gravity. Remember that it gets smaller when the distance gets bigger. So if you double the distance between two objects, you're going to cut the force of gravity between them by a fourth, because that 2's got to get squared as well. So remember those two big ideas, and you should be able to answer any question on gravitation that you may encounter. Hopefully this lesson has been useful to you. If there's any confusion or questions, let me know.